So in this section, we're going to be looking at this idea of solids, and in particular, the properties of a solid that really give them the strength and some of the electrical conductivity, let's say, of metals, the density, the hardness, all of that stuff. What occurs within a solid that allows some solid to, let's say, melt at really high temperatures or be malleable, while other solids crumble or break apart very easily. And so everything that is going to happen in this unit is going to be all about solids, and in particular, we're going to talk a lot about this idea of their crystalline structure, or better said, their lattice structure. Okay, now you recall that lattice structure is going to sound an awful lot like lattice energy, because really at the end of the day is a lattice is nothing more than a structure of some kind. So you can have a lattice, like for example, usually like a rose might grow up a lattice structure, or maybe a vine will grow up a lattice structure. A lattice is nothing more than some type of scaffolding or structure which the atoms, molecules, elements themselves will kind of bond, and in producing and repeating that pattern is then going to give the structure itself strength that on its own it may not have had. So we're going to be speaking about 4 types of solids in this unit. The first one is often referred to as crystals, right? So when you normally think of like, oh man, the crystals, right? This is usually an ionic solid. So we're thinking about cations and anions and how their proximity is going to produce Coulombic attractions, which then makes them go sink and they stick together. All right, so first we're going to talk about crystals and ionic solids. Now, another thing that actually has a quote-unquote lattice structure, or excuse me, a crystalline structure, even though crystalline wouldn't be the appropriate word here, it's more a lattice structure, right, are going to be metallic solids. So, for example, gold is a pretty hard metal. Like if I hit you over the head with a bar of gold, you'd go, ow. Lead, hard metal. Iron, hard metal. What gives these metals that are nothing more than, let's say, iron Fe atoms, or Au gold atoms, or Pb lead atoms? What gives these substances, right, in their solid form, that hardness? And the answer is going to come down to, again, they're going to have a certain lattice structure, similar to crystals, but in the case of metallic solids, we're not going to be talking about cations and anions and, attractive forces between them. Instead, we're going to be looking at this idea typically of what we refer to as a delocalized electron cloud. More on that later, so don't worry about it for now. But we're going to look at metallic solids and what is it about a metallic solid that allows it to have that hardness. And then we're going to look at some of the hardest solids out there, which are referred to as covalent network solids. Now, that first word, covalent, should give you a little bit of pause, because normally covalent bonding, like single, double, triple bonds, is not as strong as, let's say, an ionic bond or a metallic bond for that purpose. So we're going to look at what is it about a covalent network solid, such as what we find in diamonds, a bunch of carbon atoms literally holding hands. But what is it about a covalent network solid? Again, its structure that gives the diamond so much strength, right? So nothing, quote unquote, cuts a diamond except another diamond. Well, why is that? So we're going to look at this idea of covalent network solids. And finally, the last type of solid, and probably the solids that are most brittle, right? So they fall apart easily. So think of like, if you had yellow sulfur, it's smelly, but if you kind of crumble it, it'll fall apart in your hand. Or graphite, so think of charcoal, right? Like soot or ash. Again, if you had like a big chunk of it, you could just press on it a little bit and it would suddenly like kind of pulverize, form into dust, and you'd look at your hands and your hands would all be, black from the graphite. So when we talk about a molecular solid, we're going to find that these are usually the weakest, and one of the reasons for it is that in a molecular solid, we're looking at only intermolecular forces, IMFs. All the others, ionic solids, metallic solids, covalent network solids, we're talking about intramolecular forces. So for example, in an ionic solid, especially like a crystal, positive and negative Coulombic attraction, sink, they come together. Metallic solids, we're talking about a delocalization of that electron cloud, but it's all within, like from one atom to another atom, so intra. Covalent network solids, atom 1 is shaking hands with atom 2. They're forming a single, double, or triple bond. So again, intra, intra, intra. When we get to molecular solids, this is typically going to be the weaker solid or the more brittle solid, because it's only these IMFs that are not as strong that are basically holding all of our atoms together. And so because it's so important, I want to jump right in and start talking about this idea of a crystal lattice structure, okay? And in a nutshell, in a crystal lattice structure, what we're going to be looking at is something that kind of resembles what you're seeing over here on the left-hand side of your screen. In essence, what's going to happen is that we're going to create a structure formed from, it could be just neutral atoms, but let's say if we were talking about a crystal, like as in a sodium chloride, right? What we're going to find is that we're going to have one ion, which is going to be positively charged. All right, so we'll call this guy Mr. Positive. And then we're going to have another ion, a different ion, and this ion will be negatively charged. Okay? And what we're going to see is that these patterns are going to repeat over and over and over and over and over all along the lattice structure. So for example, if I made this one positive and this one negative, then what's going to happen is that more than likely this one over here, this is going to be my positive, right? And then this one over here is going to be my negative, right? And so what you should notice is that at this point, I've kind of made a square, right? And that first square that we create, this is known as a lattice unit, okay, a lattice unit. So it's like the beginnings of it. But what you could see is that if this were to continue, again, more than likely this one here is now going to be positive, right? And then this one over here is going to actually be negative, right? Because if you kind of see what I'm tracking here is I've now started to pick on the square that's here on the right-hand side. So it's kind of like, this square here, for lack of a better word, right? So it's this square here that I'm playing with. And what I'm doing is more of the same, positive, negative, positive, negative, positive, negative, positive, negative. I'm just repeating this pattern over and over and over again. And so this is what my lattice unit is going to start to do. Lattice units start to kind of work together, and as they come together, they form my first three-dimensional structure. And once I have a three-dimensional structure, it goes from a lattice unit into a lattice structure, okay? Now, why am I emphasizing this? Well, like I said, we're going to start by talking about ionic solids. And in an ionic solid, what we seem to see very clearly is that it's a bunch of these cations and anions that are being placed near one another. So let's, for a moment, forget about cations and anions, and let's talk about magnets. Let's pretend like we're 5 years old again and we're playing with the magnets in front of our refrigerator. So stupid question number one. What happens when I take two magnets, right, and I move them so they're closer together? What would the magnets tend to do? Well, if you recall, the closer that my magnets got, the greater the attractive force, until eventually if I got close enough, sink, they would jump together, right? And so one of the things that we want to have an awareness of is that when we're talking about Coulombic attraction, we're talking about the strength of a lattice structure, we're going to want to ask the question, well, how big or small are these cations and anions? Because remember, the meaning of life is size does matter. Where the smaller you are, the more attractive you are. So smaller cations and smaller anions will have a greater proximity to one another, and therefore their Coulombic attractions will be greater. So if I had to compare, sake of argument, something like sodium, let's do sodium chloride, and pick a big one, cesium chloride. Even though they both have a positive one and a negative one, because the sodium ion would be smaller than my larger cesium ion, what we're going to find is that the attraction between Na and Cl is going to be stronger. Okay? Likewise, since we're playing with magnets, let's take this a different route and let's ask the question this way. Well, what happens if we made our magnets stronger? In other words, let's pretend like I take, again, two magnets, here they are, right? And now, let's say that I could somehow make this one more positive and this one more negative, right? So I increase their attractiveness, for lack of a better word. Well, if I do that and they're this far apart, what you expect to happen is that as they become more positive and more negative, they're actually going to attract each other more. And they're actually going to tend to come together. So what happened in that scenario? In that scenario, the greater the differential in the charge, in other words, if I was +1 versus -1, as opposed to +3 versus -3, right? The greater the differential, then the greater the attraction of the charges. So when we talk about ionic solids and we talk about this crystal lattice structure, we're oftentimes going to be taking two things into account. What is the size of the ions in question? And then number two, what is the differential in their charge? So +2 and -2 will tend to be more attractive than +1, -1. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.